Introductory circuit analysis using an unconventional, intuitive approach. Session 4.
Greetings viewers.
Here we emphasize how things really work intuitively rather than blindly use mathematical methods. No mathematical background in differential equations or Laplace transform is necessary. All we need is basic calculus and working knowledge with spreadsheets such as Microsoft Excel, and familiarity with Kirchhoff's current and voltage laws, that is KCL and KVL. Please hit the like button and subscribe to our channel to encourage us to launch more videos like this. In sessions 1 and 2 we demonstrated how behavior of an RC circuit to various types of stimuli can be analyzed without sophisticated mathematical tools. We also discussed time and frequency domain analysis, principle of superposition. In session 3 we discussed diode-based nonlinear circuit. You are encouraged to review the material. In the fourth session, we are going to discuss resistor-inductor circuits. Self-inductance arises because of magnetic field generated by current flowing through a conductor. Just like the capacitor is capable of storing energy in the form of electric field, an inductor can store energy in the form of magnetic field. On the contrast, a resistor cannot store energy, it can merely dissipate energy. Self-inductance is a measure of stored magnetic energy per unit current. Inductance value depends on conductor geometry, number of turns and the intervening medium. An ideal resistor can respond instantaneously to a change in voltage as it does not store any energy. However, an inductor cannot respond instantaneously to any change in current. We are going to use this important property. Please recall this is analogous to a capacitor not being able to change its voltage instantaneously, a property used in previous sessions. The property of an inductor resisting a change in current flowing through it is quantified by the back EMF. The sign of the back EMF is such that it tends to drive current in a direction opposing the change. Let us consider an inductor carrying a constant current denoted by the red arrow. External forces are trying to reduce this current denoted by the blue arrow. Back EMF, generated between the inductor terminals, will try to resist this change, and therefore try to drive current in the direction shown by the green arrow. Therefore, the polarity of the back EMF will be as shown by the plus sign. The back EMF is a product of the inductance L, and rate of change of current dI/dt. The negative sign accounts for the phenomenon of back EMF opposing the change in current. The schematic of the series resistor-inductor circuit is shown, along with the KVL equation. Next we will use this equation to create our spreadsheet. We will enter inductance in microhenries, resistance in ohms, and time step in microseconds. The initial current through the inductor, that is before the switch is closed, is entered in amperes. We will start with a step function stimulus. Inductance in microhenries. Resistance in ohms. Just as we did for the RC circuit, let us calculate the time constant now. For an RL circuit, the time constant is given by the equation shown, namely inductance divided by resistance. It is observed that L over R has dimension of time. Time constant is calculated in microseconds. Time step should be at least an order of magnitude smaller than the time constant. The initial current through the inductor, that is before the switch is closed, is assumed to be 0 for the moment. We will remove this restriction later. As in the earlier sessions, time instants are stored in column A. Stimulus is stored in column B. Current in amperes will be stored in column D. Voltage across the resistor will be stored in column E. Voltage across the inductor will be stored in column F. Rate of change of current can therefore be calculated and will be stored in column G. Current at next instant of time can therefore be calculated and will be stored in column H. Let us consider the situation just after closing the switch. Current through the inductor cannot change instantaneously, and therefore the current is same as before closing the switch. Voltage across the resistor is the product of the current and the resistor value. Voltage across the inductor is obtained by subtracting the voltage across the resistor from input stimulus. Rate of change of current is the quotient of the voltage across inductor and the inductance value. Current at next instant of time is calculated based on value at previous instant, rate of change of current, and time step. Formulas are repeated as before. Let us look at the results now. We notice the shape of voltage waveforms across resistor and inductor have general resemblance with those in RC circuit in session 1, but are interchanged. At t equals 0 plus, the current is still 0, same as before closing the switch. For t tending to infinity, the inductor behaves as a short, and the current is simply input voltage divided by resistance R. Now let us consider the case of initial current through the inductor to be non-zero. For example, we set the initial current to negative 0.1 amps, stored in cell L1 of the spreadsheet. Note the voltage across R at t equals 0 plus becomes negative 0.3 volt, because the current is flowing opposite to the convention in our schematic. Hence, to satisfy KVL, the voltage across L at t equals 0 plus becomes larger than the 1 volt amplitude of the step function. You are encouraged to investigate the following. How does the step response compare with the results obtained by analytical method as was done in session 1? The expression for current determined by analytical method is shown. How does the time constant influence the voltage and current at various instants of time, as described in session 1? Referring to session 2, you are encouraged to investigate the following. You can create your own spreadsheet for this purpose. How does the RL circuit behave with ramp, triangle, sinusoid, and chirp waveforms? Do you expect superposition principle to work with the RL circuit? Why? It can be observed that the RL circuit can also be used as an integrator and differentiator, as was done with the RC circuit in session 1. However, the integrator output has to be taken across the resistor, and the differentiator output across the inductor. You are encouraged to compare the frequency domain behavior of the resistor-inductor integrator and differentiator by using sinusoidal stimulus at few different frequencies, as was done in session 2 for RC circuits. The analytic expressions for frequency domain behavior are given below. How does the 3 dB frequency relate to the time constant? Comparing the RC and RL circuits, we observe that both work as integrator and differentiator, and therefore exhibit low-pass and high-pass behavior in frequency domain. However, the said behavior is exhibited at interchanged points. The above phenomenon is a consequence of a more generalized concept of duality. This concludes the video on RL circuits. Thanks for a patient hearing. Please hit the like button and subscribe to our channel to encourage us to launch more videos like this. We plan to come up with more exciting videos on other circuits. Please feel free to comment or email if you have questions, comments, or need benchmark spreadsheet files. Till then, stay safe, and stay tuned.